SwayamPrabha. Digital India. Educated India.
Welcome back to our lecture series on advanced hydraulics. As we are in the fourth module on hydraulics jump, we have been dealing for last 4-5 lectures on this topic. Especially in the last class, we have discussed on jumps in sloping channels. We have also discussed on controls of jump using sills. We have also discussed how you can control the jumps using sharp crested weir. For example, like this, if you have sharp crested weir, how you can control the jump. This was discussed. Broad crested weir also we had discussed it in the last class. So, jump can be controlled using broad crested weir. So, today we will discuss briefly on control of jumps by abrupt rise in bed, also how to control the jumps by abrupt drop in bed. So, these things we will just briefly go through them, we will not have a detailed discussion on them. Then we will also discuss briefly on surges. So, control of jumps by abrupt rise. What is meant by control of jump by abrupt rise? So, if the channel flow which is being subjected to hydraulic jump, if there is a hydraulic jump, then if you are providing an abrupt rise of the bed, then how the properties behave, or what are the properties in such control phenomenon. So, in this case you have the upstream or pre-jump depth as y1, then the jump with the proper rollers and all it is there. You have the sequent depth of this pre-jump depth as y2. Then you have the height over the sill, that is the depth of water over the sill or the channel bed, which the channel bed is raised here. So, that is y3. So, you have the height of the sill as h. So, with these following parameters, you can easily see that the non-dimensional parameters you can visualize for such a condition is, there can be an incoming, for the incoming flow, what is the fluid number? You can devise y3 by y1 1 ratio, you can devise h by y1 as 1 ratio, and based on those things also you can suggest the length up to the toe of the sill as x, right. So, from Ventichow's book on open channel hydraulics, he has suggested some of the literature works in which certain relationships of fluid number with respect to the other non-dimensional numbers were given, that can be used for the design purpose, especially for control of jumps by abrupt rise in the section. So, these phenomenon, they, for example, Forster and Skrine, they have suggested relationship with fluid number as well as y3 by y1 and h by y1. They can be given in the following. They suggested it especially at a length x is equal to 5 times h plus y3. So, this thing here, if I can plot them, the equations or the graph that can be used for design. Here on the x axis, on the horizontal axis, you can have fluid number. Fluid number, it can be 1, 2, 3, 4, 5, 6, like that it can extend. Then you have the non-dimensional number y3 by y1 in the y coordinate. Two hashed lines are drawn here. Here the first one suggests, I will just change the color for your benefit. This line suggest for the depth y3, which is equal to critical depth. If you recall the figure, earlier figure, this is y3. So, if the flow over the sill, if it is critical, that is after the channel bed has been elevated, whatever flow depth, if it is critical, then that could be the minimum possible, means you cannot go beyond that in such a situation, for whatever elevation it is there. For such a control for measure, definitely it cannot go into the supercritical condition, right. Means you are providing jump from supercritical to subcritical conditions. Later on it cannot come back into the supercritical again. So, that is not advisable. So, critical depth is a minimum possible condition here. Okay. So, here y3 is equal to yc, that condition can be incorporated. Then I can suggest one more line here. Here the depth y3 is same as the depth y2. So, just go back into the figure. This depth y3 is same as y2. What does that mean? That means there is no elevation in the bed here. At the section x, the elevation provided is 0. Then only you can have y2 same as y3 in such a situation, right. So, these are the maximum condition or the bound maximum possible phenomenon for such a thing, right. So, within this you can plot various curves that can be used for design processes. For example, this one particular curve I would like to draw is, say, one curve which starts from here, it goes on like this, another curve goes on like this. So, these are all individual curves for various ratios of h by y1. So, let us say this is h by y1 is equal to some numerical value a, h by y1 equal to some numerical value b, h by y1 is equal to some numerical value c. So, definitely a is less than b, it is less than c in this design criteria. So, if you have such things, then for the given condition you can easily plot or you can easily find what could be the post means what could be the tailwater depth easily. Say for h by y1 curve, if one curve it is given to you and if the incoming fluid number is somewhere here, just check what is the depth. So, you will get the corresponding y3 by y1 ratio or y3, like that you can infer for the design purpose. So, the worst possible scenario in this case is abrupt rise in abrupt scenario in the abrupt rise in bed is y3 is equal to y2, that is there is no elevation in the bed. Now, as the jump comes, so this is y3 is equal to y2 curve, and as said earlier y3 is equal to yc curve. These are fluid numbers and y3 by y1 on this axis. So, the jump consists of supercritical flow upstream. Now, if you just see for any of this curve, as we have drawn several curves, what happens? Y3 is equal to yc. At y3 is equal to yc, the jump consists of supercritical flow at the upstream. I am just again redrawing the thing here. So, supercritical flow, jump occurred and the subsequent flow is denoted like this. So, this is the jump. So, you have supercritical flow before the jump, subcritical flow after the jump. So, the critical conditions are overcome within this jump, right. It is transforming from supercritical to subcritical in the jump. So, the maximum raise of bed is possible is the flow depth here should be critical. You cannot design any raise of the bed beyond this thing. If it goes beyond this thing, it may affect the hydraulic jump considerably. So, that is one criteria you need to remember always. Next, which we would like to deal is the next topic which we are interested is control of jump by abrupt drops. As you have studied in the abrupt rise case, similarly abrupt drop cases are also used for controlling various hydraulic jump. For example, just recall the things in the sharp crested weir, broad crested weir as well as the abrupt rise in channel bed. What were the situations that for which all situations you use these mechanisms to control the hydraulic jump? Usually, if the downstream depth, previously just go through, if the downstream depth, these cases, if they are less than the sequent depth of the hydraulic jump, you can definitely see here, this is y 3 is less than y 2 here. So, if such situations are there, mostly in most of the cases, if the downstream depth is smaller than the sequent depth, then the above mentioned sharp crested weir, broad crested weir or abrupt rise in channel beds are used. What happens if it is the other way? You have already studied how the hydraulic jumps are affected by the tailwater condition. So, if the tailwater depth or if the post jump depth, if it is higher than the sequent depth of the if the tailwater or the downstream tailwater depth is greater than the sequent depth, then the pre-jump depth of the water, how it can be related with the hydraulic jump. So, you have the pre-jump depth as y 1 here. Now, this depth is y 3, okay, and the bed dropped is h. So, with these following cases, you need to provide a drop in channel flow, so that this jump occurs. If you are not providing such a drop in the channel flow like this, then this jump cannot occur in this place. It may get shifted to some other place that you have already seen. So, that way to ensure proper occurrence of hydraulic jump in this location, you have to provide the drop in elevation. When you do the control of hydraulic jump by abrupt drop in the bed, you need to remember the following things. You need to remember, for example, say if I just draw the water surface elevations. So, you have the water surface elevation. So, jump if it goes like this very much upstream, if it is like this, say if this is the maximum elevation possible. Suppose if the jump is occurring in this way, there are chances that this jump may move upstream. So, this jump may move upstream. There are chances for that. Then there are certain jumps where the jump may be like this. When you have provided such a drop, the jump may have just occurred like this. So, here the jump is pushed downwards. Okay. So, here the jump may travel upstream. In another case, for the same fluid number, that is what, for the same incoming flow based on the rise, based on this elevation, the jump may be either moving upstream or it may be pushed downwards or it may be held within this section. Okay. So, for the first condition 1 here and the second condition given here, for the first and second condition, definitely the control by abrupt drop cannot be used, because your jump may be either pushed downwards or it may be it may travel upstream. So, you cannot use this particular control measures. So, these jumps are only feasible for conditions where the hydraulic jump is within certain limit. Okay. So, it is not undulating or it is not too high something. So, for those cases only you can use this, where if the stilling basin is provided along this ridge and all, you can ensure that the jump occurs in this region only. So, with this we would like to conclude the control of hydraulic jumps. Now, the next topic which we are going to deal is, may I beg pardon, I just forgot to mention, you can also design curves for abrupt control of hydraulics, control of jumps by hydraulic jumps by drops provide. So, here also we can say for the incoming flow fluid number or the pre-jump fluid number, ratio y3 by y1. For the various cases, say h by y1 is equal to a, h by y1 is equal to b, h by y1 equal to c. For different values of this particular ratio h by y1, a, b, c, where a is greater than b, it is greater than c, like that. So, if you have such design, if you have such standard curves and all, these curves can be employed for the design of the design of the sills and all, so that the jump occurs in that particular location. So, you can easily say for the given fluid number, if the h by y1 is some value c, you can see that the corresponding y3 by y1 ratio is so and so. So, the y3 depth is like this. Like this you can easily manipulate and use for design purpose. So, next, as I told earlier, we are going to go through the concept called surges. What is meant by a surge? Surges are also called moving hydraulic jumps. Precisely for that particular reason only, we have incorporated this topic in this particular module. Actually, frankly speaking, this could have been, means we could have made another module of this course where unsteady flow could have been incorporated in the entire course this thing. However, as per the syllabus given or as per the syllabus devised for this course and all, a separate module on unsteady flow is not being suggested, but still we will be dealing with this topic called surges, that are called moving hydraulic jumps. The rapidly varied flow, in the earlier cases we have studied the rapidly varied flow in steady state conditions. So, if the rapidly varied flow is in unsteady condition and involves rapid changes from supercritical to subcritical, then such quantities are called hydraulic surges. Okay. So, such quantities, that is the rapidly varied flow is unsteady, it is unsteady and involve rapid changes in stage from supercritical to subcritical and vice versa. So, those are called surges, or usually it is called surges. Waves, in waves it is more gradual in nature. So, that we are not going to study right now here. What is the peculiarity of surge? If there is an observer, say if there is an observer standing here on the banks, and if he moves with the same velocity of a wave, say here you can see that the water is rising like this at this instant, and then it is traveling like this. Okay. So, after a few minutes, this would propagate up to here, right. So, in this case, this is called a wave, or the water height, it is not constant, it is